force using vectors. So let's visualize a 3D space. So here's my X, Y, and Z. And let's consider some object in the XY plane. And there's a force that is being exerted. And let's label that as F. And this object, let's say, is pinned at the origin. So what we want to know is what is the moment about point O, or about the positive z-axis, due to this force F. So the formula is as follows. The moment about O is a vector determined by a position vector r, and you cross it with the force vector F. This position vector is any position vector from O to any point on the line of action of F. So I draw my line of action for F, and I can draw any position vector now from this point O to any point along here. So I could say it's that, or I could even say it's that. There's an infinite number of possibilities on this position vector. In other words, the moment about O is given by R1 cross F, and that will also equal to R2 cross F, as well as R3 cross F. Make sure that you don't write something like this, F cross R. This is wrong. You have to have it in this particular order. Let's move on to the magnitude of the moment. So recall A cross B was equal to a vector C, and we said that vector C has a magnitude of the product of the magnitude of these two vectors times the angle or sine of the angle between them. So let's rewrite this specifically for our situation here. So we would have R cross F is equal to our moment vector, and the magnitude of my moment vector would equal to the magnitude of my position vector multiplied by the magnitude of my force and the sine of the angle between them. In terms of direction of a moment vector, we use the right-hand rule. Let's consider the following system. Let's say I have an XYZ coordinate system like this, and I have an object that lies in my XY plane. A force is applied as such. And now what I want to know is what is the moment of this force about point O. I can now draw the line of action of that force, draw any vector from this point of rotation to any point along the line of action of F, and I get this. To determine the direction of the moment vector, we use the right-hand rule. you direct your fingers along the position vector and you sweep it in the direction of the force, giving you the moment vector that points upward or is in the z direction. Again, R cross F means you take your fingers, put it in the direction of that position vector, sweep your fingers in the direction of the force vector, and the thumb indicates the direction of your moment vector. So in this case, our moment vector points upwards, and it has a counterclockwise rotation. Here's an interesting note about the magnitude of the moment vector. So consider again this x, y, z coordinate system. So x, y, and z. And suppose we have that same body here and a force is being applied to it. And we have this position vector. Let's say it's this. Okay, so that's my position vector. And we said that the magnitude of this moment vector due to this force F about 0.0 is given by the magnitude of R times the magnitude of my force vector times the angle between it. So what I have to do is draw this extension line, and this would be the angle between the two vectors, theta, and this would also be theta. I'm going to rearrange this and write it like this. The moment about O is the force vector, the magnitude of the force vector, times r sine theta. Now this r sine theta is actually the perpendicular distance from O to the line of action of F. That means it would be something like this, where that's 90 degrees. So if I were to determine this length, which is a perpendicular distance from point O to the line of action, to a point on the line of action of force F, this would be given by sine of theta is equal to the opposite, so over the hypotenuse. So D perpendicular is R sine theta. Isn't that interesting? Right there. Now what we want to do is calculate the resultant moment. That means within a given system, let's say x, y, z, there's some kind of 3D object, and there are multiple forces being applied to it. Let's say that's F1, and let's say this is F2, and this is F3. And these are all three-dimensional force vectors. And what we'd like to find is the resultant moment about 0.0 due to all three forces. So we apply the formula as such. The resultant moment about 0.0 is given by, and of course that's a vector of, I can select a position vector anywhere from 0.0 to anywhere along the line of action of F1. Same thing for F2. I can determine a position vector, R2. Likewise for F3, R3. So the resultant moment about point O due to all three forces is given by the sum of R cross F.